Programming movie 4.2. So we were talking about these numbers that are embedded within our code, and some of them may be fine left as they are, especially if we only use them once, like for example where we set the colors. But other hard-coded values might cause a problem later on, because if we want to change that value and it's embedded a large number of times throughout our code, then it could cause issues. So imagine if, for example, you were building, say, a retail system in which we'd embedded the value for sales tax or VAT to, say, 20% throughout the code. If that number is embedded throughout the code, if the budget changes the rate of sales tax, either up or down, then we have to hunt through our code and change every single instance of 20 to, say, 21 or 22. And if we miss one instance, then we'll be calculating sales tax or VAT incorrectly somewhere, which means that people will be either undercharged or potentially overcharged, and that will have a predictable impact on your employment once your boss finds out what you've done. Also, these numbers aren't particularly meaningful. It's not obvious from looking at the code what the 45 actually means. Remember, most code that's written has to be maintained by someone other than the original author. So it's a good idea to make your code as easy to understand as possible. And even if you have to go back to your own code yourself in 6 months' time, your older self will not thank you if you've made it hard to understand. After that sort of delay, you're effectively looking at it as if you're reading it for the first time. So we need to come up with a way of avoiding having to replicate the same hard-coded number over and over again for the same basic meaning, whilst also ensuring that our code is sort of comprehensible. So luckily there's a facility in processing and other languages called the constant, and this allows us to create data items with a name or a label and a value, but the value isn't expected to change, so it remains constant. Because they're not variable, that's why we call them constants. We denote this by saying that they have a final value. So when we declare constants, we modify the declaration with the word final, and I'll show you an example of that shortly. So here we have basically the same code as before, only this time we've introduced a bunch of constants. And these are just data items that are declared as final. So whenever you declare a constant, you simply say final first of all, and then the normal declaration. Okay, and you can't change these values anywhere else. So we have one each for the width and height of the canvas, one for the size of the ball's border, that is the ring of pixels around the outside. One for the ball's diameter, 45 pixels, and two for the start location of the ball. So all of these numbers previously were sort of hard-coded into the code, and now they're sort of separated out into these constants. So if we want to use constants to change, or indeed variables to change the canvas size, we need to use an additional pre-supplied function called settings to do that. So we can't change. If we want to use raw values, then we can just do that in setup. But if we want to use variables and constants, then we need to use the settings function, which is again pre-supplied with processing. This is just a minor technical requirement. So in setup and in draw, you can see here how we reference these constants, and I've included the original code off to the side here just so you can see the difference. The code with the constants is longer, but I think it's much better because it's much easier to understand and it's almost self-documenting. So constants have two main benefits. Again, it makes the code easy to understand, but it also means that if we want to change something, say the diameter of the ball, we only have to do it once. We do it once at the top of the code here, and then wherever we reference the diameters, you can see here we've got ball diam referenced 4 times in this code. If we were just to leave the 45 in hard-coded as it is, then we'd have to change 4 different instances of ball diam. But whereas if we use constants, we simply have a single reference to the diameter of the ball here, and then reference it using the label, so that if we ever want to change the size of the ball, we just do it once there, and then that change automatically is reflected in these calculations here. So the code for this is on Blackboard, so have a play with it and experiment. Maybe change the diameter of the ball and so on, just so you get a feel for how those changes ripple through. So I want to just talk about the bouncing ball question from the workshop last week. So you'll recall that I asked you to write code to draw a ball bouncing around the screen. So it starts in the top corner, say at 150, heading southeast, that is down and to the right. And if it reaches any edge of the screen, top, bottom, left or right, it reverses its direction. Now, we don't necessarily expect you to be able to do that yourself straight away, but we just thought we'd pose it as a challenge. But don't worry too much if you weren't able to get it working, because it was quite a hard question for you. So here's basically what we were trying to achieve. So here's the ball. The movie capture wasn't as smooth as it might be because my machine was quite laggy, but you get the general idea. There's the ball bouncing around the screen, and when it hits the edge, it sort of it reverses its direction. So if we watch this video, what sort of general pattern did we observe over time? What sort of analysis of what we see allows us to come up with an algorithm for that problem? Well, the general pattern is that the x and the y coordinates of the ball only change by 1 pixel at any one time step. So they only ever change by either +1 if it's going either to the right or down, or -1 if it's going to the left or up. So this means that we're essentially adding an offset of either +1 or -1 to each of the x and y coordinates at every time step. So just to sort of clear up what I mean by this, if we look at the ball, then at every time step, because it's moving diagonally, both its x and its y coordinates will change, and they only ever change by either 1 pixel up or 1 pixel down. So if the ball moves down and to the right, we add 1 to the x and 1 to the y. Remember, the origin is at the top left. And if it moves down and left, we subtract 1 from the x and add 1 to the y. So if it's moving down and to the left, so we take 1 off the x and add 1 to the y, and so on. And this allows us to control the direction of the ball, not just when it's moving regularly, but when it hits the edge. Because if we flip the value of an offset, say the x offset from positive to negative, then we reverse its direction. So here's the basic algorithm for this bouncing ball. We set up a bunch of variables to store the x and y coordinates of the ball and the offsets. Okay, so these offsets are basically either +1 or -1 values that we add to the x and y at every time step. And then we set the coordinates, and then we initialize the offsets, and then we set up the graphics, and then in draw forever we essentially clear the background, so that wipes it, clears the canvas, and then we move the ball by just adding the offsets to the x and y. Okay, so by adding either +1 or -1 to each of x and y, we basically move the ball diagonally. Then we have to do the collision detection. So the collision detection is basically 4 if statements, each of which corresponds to one of the boundaries of the edges, boundaries of the canvas. So if x is near the right-hand edge of the canvas, then in order to reverse the direction of the ball, we simply set the x offset to -1, which means move the ball to the left. If x is near the left-hand edge, then we set the x offset to +1. Okay. If y is near the bottom of the canvas, then we set the y offset to -1, that is, move the ball up. And if y is near the top edge, set the y offset to +1, that is, moving downwards. And then we draw the ball. So here's the actual code for the draw method. the draw function, and you can see how it's very straightforward. So you think, oh, I'm never going to work out how to do this sophisticated bouncing code, but it's actually very straightforward when you know when you understand the problem. So here we clear the background, then we add the offset values to x and y, which essentially moves the ball. Then we do the collision detection. So basically, if the x coordinate of the circle is greater than 455, that is, it's close to the right hand edge, then we set the x offset to -1. That is, we flip it. So next time around the loop, we add -1 to the circle x, so that's essentially subtracting 1 from circle x, so it starts to move to the left, and so on. And you can see how we do exactly the same with the left hand edge, the bottom and the top, and then we simply draw the circle. Now the keen-eyed amongst you will notice that I've gone against my previous rules of using hard-coded values in there, but please try to overlook that. Now, you'll notice how I've also put comments in the code. So here, here, and so on. So these are just little notes to myself to help understanding. So anything after 2 forward slashes is ignored by the system, which allows us to add useful information into our code to make it more readable. And make sure that you do this a lot with your code, because you'll thank yourself when you have to come back to your old code later on, and also it makes it easier to read for other people. So always comment your code liberally, doesn't cost anything, and it will save you a lot of trouble and time later on.